a rather trivial differential equation over here. The question is, can you construct finite difference approximations to this differential equation? And you can do that both using forward differences, backward differences, and central differences. So pause the video and see what sort of finite difference schemes you can come up with. Let's start with the forward difference scheme. So for the forward difference scheme, we're going to make use of information from the current point and the point in the future. So if we need to calculate the derivative at a certain point in time, so if we need to calculate du dt at the time point n, we're going to approximate that by having un plus 1 minus un divided by our time step delta t. And on the right hand side we have obviously minus a, the value of u at the time point n. So very easy, we now have an equation which you can use to extract un plus 1 as a function of un. So that basically gives us that un plus 1 is equal to, okay, so bringing the delta t to there and then bringing this thing to there, giving us un minus a delta t un. So finally, we can write that un plus 1 is 1 minus a delta t multiplied by un. So this shows you how to move from the current time step to the next time step simply by multiplying by this constant over here. This method, which we construct from the forward differences, is called the forward Euler method. Now, what I suggest you do is use the backward difference approximation to construct the backward Euler method. So pause the video and see what you get. So for the backward difference approach, if we approximate our derivative at time step n rather, so du dt, now we don't look towards the future and the current point, we rather use the current point and the past point. So this becomes un minus 1. And again, we divide by delta t is equal to minus a un. Now, in order to make it a little bit easier to compare these two formulas, let's just shift the index here by 1, so that in both cases we have something involving un plus 1 and un. So it's in essence just a cosmetic operation. So if we shift from n to n plus 1, we have that un plus 1 minus un divided by delta t is minus a un plus 1. And again, let's calculate un plus 1 here explicitly. So un plus 1 is equal to un minus a delta t un plus 1, or un plus 1 is equal to un divided by 1 plus a delta t. So in this case, we have something in the denominator. Okay, so this is the scheme we have for the backward Euler method. What we're going to do now is do something involving the central difference approximation, which is more accurate, second order accurate. So in order to do that, we're going to calculate the derivative in some in-between point between n and n plus 1. So let's call that point n plus 1/2. So let's calculate the derivative there. And then we, strictly speaking, do not know what the value of un at that point 1/2 is. But what I suggest we do is we just assume that in between 2 points, the value that we have is just the average of the 2 neighboring points, which we do know explicitly. So pause the video and see what scheme this results in. Let's calculate the derivative in our intermediate point. So un prime n plus 1/2. Let's approximate that by looking to the future, but also by looking to the, by looking to the future, that's n plus 1, and then looking to the past, that's just n. And then we need to divide that by the time step which separates these 2 points, so that's just delta t. And then for the right hand side, we have minus a, and what we've done, we've evaluated our derivative in this point in between, so this should be a u n plus 1/2. And again, we do not know what u n plus 1/2 is, but we can just say it's the average of u n and u n plus 1. Good. So now again, we have an equation which we can use to extract u n plus 1 as a function of un. So let's simplify that. We have u n plus 1 minus un is equal to minus a delta t over 2 un, and then minus a delta t over 2 un plus 1. So the un plus 1 appears here and there. So we can write that un plus 1 is equal to 1 minus a delta t over 2 divided by, and then we have 1 plus a delta t over 2 un. So in this particular case, our scheme looks a little bit more complicated, but it's much more accurate. It's second order accurate because we have information both from the future and the past that we incorporate. This particular scheme is called the Crank-Nicolson scheme. Now, if you look at the 3 equations that we've derived, they all look kind of similar, and actually you can combine them and you can unify them in some sort of generic scheme, which reads as follows: un plus 1 is equal to 1 minus 1 over theta, a delta t, divided by 1 plus theta, a delta t, un. So as a final quick step, pause the video and see which values of this parameter theta correspond to each of the 3 cases that we've discussed. Let's see what happens when theta is equal to 0. So if theta is equal to 0, we basically don't have a denominator, we only have a numerator. Let's go back to our forward difference case, and this is indeed what we have there. So the case where theta is equal to 0, that corresponds to the forward difference case. If we have theta equal to 1, then in essence we only have a denominator. And if we compare that to what we had up there, we indeed see that the case theta equal to 1 corresponds to the backwards difference, to the backwards Euler. And then finally, theta equal to 1/2, that's the central difference approach leading to the Crank-Nicolson methods. And this gives you these factors 1/2 here. So this is how you can calculate finite difference approximations to this very simple differential equation.